So this is a shorter video on how the ozone layer is broken down by nitrogen oxides rather than CFCs, but it undergoes the same radical substitution mechanism. You need to know the mechanism as it's very easy to learn, as it's the same as the one for the CFCs with some minor changes. Just to remind ourselves that ozone is produced in the upper atmosphere, in the stratosphere, when oxygen molecules are broken down homolytically by UV light. So the double bond breaks in oxygen and we have diradicals. So these are diradicals as they have two unpaired electrons as shown on the electron configuration. The ozone produced is at the same time broken down back to oxygen in a dynamic equilibrium where the rate of the forward reaction is the same as the rate of the reverse when there's no pollution, such as CFCs. So this is called a steady state. Before we look at how nitrogen oxides break down ozone, let's recap how ozone is broken down by CFCs, because the mechanism is virtually identical. So CFCs, like this here, can break down under UV light to form chlorine radicals. The chlorine radicals from this initiation collide with ozone in the upper atmosphere and form oxygen, and we can work out this radical by balancing this step. This radical propagates or proliferates more radicals. These collide with oxygen diradicals in the upper atmosphere, which are formed in the reaction shown in this steady state equation. They produce oxygen and regenerate the chlorine radical, which go into the first propagation step. So this will continue a chain reaction. Combining two propagation steps, we get this overall equation, which is the breakdown of ozone to oxygen. So this catalyzes the breakdown of ozone back to oxygen in the steady state equation, and we have a reduction in the concentration of ozone in the stratosphere. The ozone layer is not only depleted by CFCs, it is depleted by also nitrogen oxides. Nitrogen oxides, as the name suggests, contain nitrogen and oxygen, and they are formed when nitrogen in the air and oxygen in the air combine at very high temperatures. Very high temperatures are needed as the activation energy for the reaction is very high, as the nitrogen-nitrogen bond is a triple bond and the oxygen-oxygen bond is a double bond. So lots of energies need to break these bonds before they can react. At high altitudes near the ozone layer, the most likely sources of this energy comes from lightning strikes and the intense heat of jet engines. The nitrogen oxides produced are radicals, as each of them have an unpaired electron. We're going to look at the radical substitution mechanism for this reaction. We're going to skip the initiation as the radicals are produced by physical processes. I've copied here the mechanism by which ozone is broken down by CFCs, because the nitrogen oxide breaks down ozone in a very similar propagation step. As I've said, I'm going to skip the initiation step as the nitrogen oxides are produced by physical processes. So we're only going to draw the propagation steps for the breakdown of ozone by nitrogen oxides. So we'll start with ozone in the same way as in the propagation step for the breakdown of ozone by chlorine radicals from CFCs. So instead of chlorine radicals, we have nitrogen oxide radicals, and these are going to produce oxygen in the same way as in this mechanism. So what we'll do next to find out what's here is to balance this step. So we have 4 oxygens on the left, but only 2 here. So this species must have 2 oxygens. We have a nitrogen on the left and a radical, so this must also contain nitrogen and must be radical, which is what we expect, because a non-radical and a radical should give us a non-radical and a radical. So the radical produced should be this. We then take this into the second step, and hopefully remember that each of the propagation steps will produce O2, similar to the one in the CFC's mechanism. We are going to regenerate the radical in the first step to produce a chain reaction. And finally, we find out what's here by balancing this step. So we have nitrogen on both sides and radicals on both sides. We have 2 oxygens here and 3 here. So this will be the oxygen from the steady state reactions in the upper atmosphere, which is identical to this step in the mechanism for the breakdown of ozone by CFCs. So these two mechanisms are virtually identical. The only difference is the radicals. So if we combine these two steps and cancel out the spectators, which are the radicals, we get the same overall equation as with the breakdown of ozone by CFCs. This is how nitrogen oxide catalyzes breakdown ozone to oxygen. Nitrogen oxide is a catalyst because it's regenerated in the second step. So now we know the mechanism by which nitrogen oxide breaks down ozone. We've completed all the topics for haloalkanes in the first year.